Hey guys, so today we're going to talk about the photoelectric effect and how it pertains to quantum mechanics. We're going to get into quantum mechanics and nuclear physics over the next, week and a half, 2 weeks. So we're going to start off with the idea that, the question is light a wave or a particle? And the answer is yes. It actually has properties of both. And we're going to talk about those properties. We've talked about actually 4 of those properties already, but we're going to get into not just wave properties of light, but also why scientists believe that it also has a particle nature and acts like a particle as well. It has a wave-particle duality. So when we look at some different properties like reflection, refraction, interference, diffraction, polarization, and photoelectric effect, we can basically see whether does that property mean it acts more like a wave or a particle. Okay, so what you have to ask yourself is, can waves be reflected? And that is true. So we're going to put a little check mark here. Okay, can particles be reflected? Well, yeah, you could shoot a Nerf ball, like a dart out of a Nerf gun off a wall. It'll reflect off. So that's a particle. Particle property is for reflection. For refraction, okay, remember refraction means that as you enter a new medium, your speed changes. Okay, so as you go from, say, less dense to more dense or more dense to less dense, you actually can change direction. Okay, waves can do that. We know waves can refract. Okay, and particles can too. If you take a particle, just like I said, think of like a ball that you're throwing or something, and you're throwing it into water, from air or something like that, then it'll slow down and it'll change direction. Interference, can waves interfere with one another? Well, yeah, we know waves can interfere. Okay, they can exhibit interference patterns. Now, particles can interfere, but they don't exhibit the same interference patterns. So when we talk about light, we know that light exhibits those interference patterns when you have more than one wave that interacts. Remember when we talked about interference as it pertained to Young's double slit experiment? And so I guess technically you could say particles interfere with one another too, so we'll put a little checkbox there. Diffraction, remember diffraction is when you bend around a barrier. Okay, remember if you have a single slit experiment and you have light coming through, those waves can bend around the barrier. Okay, versus a particle, it either hits the barrier or it moves through the barrier. It's not going to bend around the barrier. So waves can exhibit diffraction properties, but particles cannot. Okay. Polarization, I know we haven't talked about that really at all. It's the idea that because light is an electromagnetic wave, it has an electric component and a magnetic component. And you don't really have to know about polarization. That's not something that is, part of the objectives for AP Physics, but it's still an important property to know. The idea that you can take a filter and you can line it up with either the electric portion or the magnetic portion of a light wave, and you can filter it out. Okay, and by lining up more than one of these filters, you can actually cancel out light. But you don't have to cancel out all of it. You can either cancel out the electric wave portion or the magnetic wave portion. So waves do exhibit polarization-like properties. Particles do not, because they don't have. You can't just polarize half of a particle like you can polarize half of a wave. Photoelectric effect. So right now, if we take a look, it looks like we've got a lot of evidence showing us that light is a wave and not a particle. Because every single property that we've talked about tells us that waves exhibit those properties, except for the photoelectric effect, okay, which we'll talk about in just a minute. Okay, so it's this idea that yes, light exhibits these properties, but light also exhibits properties of particles as well, so it actually acts like both. So as you can see, the notes I gave you, so that we didn't have to just write down a whole lot, I'm just going to do a little bit of reading here so that the videos wouldn't be 50 minutes long. So there were experiments done that classical physics couldn't explain, like the photoelectric effect. It was found that electrons and photons could only exist possessing discrete amounts of energy, period. We're going to focus on the energy stored by a photon. Okay, so a photon, think of it as a wave packet of light. So when I draw a photon, think of it like a wave. It has a wave nature, okay? but think of it as a packet of waves, okay, like a discrete packet of waves. So the amount of energy that's stored in that discrete packet of waves, also known as a photon, is dependent upon the frequency of light. The key idea here is that energy is quantized and only can be found in discrete packets, okay? So the amount of energy stored within a photon is going to be equal to Planck's constant. This right here is Planck's constant, which is on your constant sheet, and it's 6.63 times 10 to the minus 34th joules times seconds, okay? It'll always stay the same, always use the same constant, and this is your frequency of light, of your light, obviously in hertz, and this is energy in joules. Okay, so given a specific frequency of light, it can only possess, per photon, per energy packet, it can only possess a given amount of energy in joules. Okay, so the photoelectric effect, that basically the effect that allowed us to see that light also acts like a particle. Einstein won his Nobel Prize based on the explanation of this effect. The cool thing about Einstein is that he didn't do experiments. He wasn't an experimenter. He was a theorizer. And so he left the experimentation to everyone else, and then he just explained everyone else's stuff and got Nobels for it. So everyone thinks he won the Nobel for relativity, but that's not the case. He won the Nobel for this idea that light is a particle. The effect was first discovered, meaning like the experiment was done by Hertz, but Einstein was the first to successfully explain it. So, when light hits a metal surface, this is the idea, okay? You have a metal. Light hits a metal surface. And we say metal because metals loosely hold their electrons. They usually have a lot of orbitals away from the nucleus, and their electrons are kind of loosely held. So there's electrons in here, okay, in the metal. They're kind of loosely held. And light, okay, little packets of light here, photons, hit the surface, okay, and it takes a certain amount of energy to release those electrons, okay, and it's dependent upon the metal, okay, it's dependent upon the metal. The metal absorbs a certain amount of energy in order to get those electrons out of their orbitals and allow them to be ejected. So this photon has a given amount of energy, E, okay, and it's going to strike this metal. That metal is going to absorb some energy, and the amount of energy it absorbs is called the work function. Energy the metal absorbs to release the electron. So basically, it has to absorb a specific amount of energy to release it. If you've reached that threshold, say it takes 5 joules to release it, if you've given it 5 joules, then that electron is going to be ejected. Okay, and we call it a photoelectron. It's still an electron, we just give it a name like photoelectron. So light hits metal. It takes a certain amount of energy to release that electron. That's called the work function, and that's dependent on the metal. It's dependent on metal. So silver is going to have a different work function than, say, gold or something. And then an electron, if you've reached that threshold, that amount of energy that it needs to release it, an electron is released. And it has a certain amount of kinetic energy called Kmax. They call it maximum kinetic energy that it has. Okay? So example. Let's see if we can get this up here. Silver has a work function of 8 joules. So let's say it takes 8 joules that you have to add before anything can be released. Silver has a work function of 8 joules. If a photon hitting it so if this photon coming in has 20 joules of energy, then the electron that's freed will possess 12 joules. That makes sense, okay? So if this has 20 joules coming in and it takes 8 joules to release it, then this guy going out is going to have 12, okay? So the question is, well, what if we don't have enough energy to overcome the work function? What if the photon coming in only possesses 5 joules of energy? Well, guess what? That electron is not going to budge because there's not enough energy to release it. Okay, so we have an equation that represents this relationship. the amount of energy that the electron's going to have after it's ejected. So this is the energy electron has after it is ejected from the metal. That's going to be equal to however much energy that the photon is going to have as it hits the metal. So this is the energy of the photon. Energy of the photon minus however much energy it takes to release it from the metal. Okay, this is the work function. This is the amount of energy it takes to release it from the metal. This is all pretty intuitive. Okay. So think of this as the energy of the photon, this is the energy that it takes, that you have to overcome in order to release the electron, and this is the leftovers. This is the leftover energy that the electron can possess. And guys, if you don't overcome, if you're not overcoming whatever energy it takes to release it, that electron's never going to get ejected. Okay. What's cool about this is that this shows the discrete particle nature of light. Because if light was a wave and the amount of energy that it possessed was continuous, not quantized, then that would mean that it wouldn't be dependent upon your frequency. You could have any amount of energy that you could add, kind of like a range of energy that you could add, and it wouldn't be coming in these discrete packets, okay, which lends itself to the particle nature, okay. So the cutoff frequency, also known as the threshold frequency, and it's denoted by a little f sub 0, is the minimum frequency that a photon can have and still cause the emission of photoelectrons. So it's like right there at that threshold. So the work function, the amount of energy it takes to release that electron, is equal to Planck's constant times whatever that threshold frequency is. The minimum amount, like what is the bare minimum? What is the bare minimum frequency that light can have in order to release it? And this is the equation that you would use for that. Okay. So the cool thing is this is how like solar panels work. Light hits the metal on the solar panel, releases electrons, and this creates current. You can get electricity out of this, which is pretty cool. So the released electrons create current in a circuit. Voltage can be applied to this circuit to oppose the current flow. So if you have, current flowing, you can apply some voltage V. We call it the stopping voltage, also known as stopping potential, retarding potential, okay, V sub S. You can apply that, and that energy, which remember, energy relates to voltage by QV, okay, that energy that you provide to that circuit that has electrons flowing through it is going to oppose that flow. Well, basically, whatever energy that you have to add, QV, in order to oppose that flow is going to be equal to the amount of kinetic energy that electron has, okay? So the amount of kinetic energy that it has, Ke max, okay, is, in this case, if you apply some voltage to try to get those electrons to stop, those are going to be equal, okay? So the amount of energy the electron will possess will be equal to its charge times the stopping potential, okay? All right. A couple other things. Another unit of energy that we haven't really talked about is the electron volt, okay? EV. EV is the unit. And this is basically, you can relate this to joules. It's equal to the amount of work done to accelerate an electron through a potential of 1 volt. Okay, QV, right? We just talked about that. And basically, 1 electron volt is equal, think of it like this. Where's my sheet at? Is equal to 1.6 times 10 to the minus 19th joules. So not a coincidence. Remember, this is your charge on an electron, so it should be really easy to remember. Okay, this is your conversion factor, which you're going to use a lot. Okay, because sometimes it wants to know, well, what is the amount of energy stored in electron volts? Okay, so 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. Here's the conversion right there. okay? As you're going to find out in a PhET that you're going to do tomorrow, your Ke max is independent of light intensity. It is dependent on the frequency of light, though. Intensity and frequency are not the same thing. Remember how amplitude, how it related to sound is different than the frequency of sound? Same thing. So think of it like this, guys. X-rays are going to have a lot more energy than, say, infrared, okay? And so think of, if you were bombarding a surface with X-rays, think of that as like shooting a gun at it, with like a bullet, okay? Lots and lots of energy, okay? You could shoot one bullet or you could shoot 1,000 bullets, okay? 1,000 bullets would be greater intensity. You're still going to have really high energy because of the frequency. Low energy radio would be like shooting, instead of shooting a gun, shooting like a Nerf gun with like a little Nerf ball. You could shoot one Nerf ball or 1,000, and you're still not going to have a whole lot of energy per unit photon or per unit ball, okay? All right. Also, before we get to the example, I'm going to put this graph down here. You're going to see some graphs, okay? Really two main kinds of graphs. Oh, there goes my dog's barking. You're going to see the Ke max versus frequency graph and voltage versus frequency. Those are the most common that you're going to see when it comes to the photoelectric effect. And this is what the graph looks like. Okay. And it's the idea that this right here stands for that cutoff frequency. Okay. You're looking at basically the amount of energy that that electron's going to have versus the frequency of the photon that's hitting the metal. Your x-intercept represents the cutoff frequency. And if we look at our equation, let's look at y equals mx plus b form. Your y value here is your K max. Remember, this is your y-intercept. That's going to stand for your work function. So if you extrapolate this out, this right here is your work function of your metal. It looks curved. Sorry, I need a ruler. But there you go. That's your y-intercept, which means that your x value is your frequency, which means your slope is Planck's constant. It's a very popular question right here. Very popular question that they like to ask, especially on free response, is, how can you find the slope of the line? And really, you just use your values that are given from the graph, and Planck's constant will be your slope. Constant will be your slope, okay? Another way you might see the graph is voltage versus your frequency. And as you recall, Ke max, when you do subject it to some sort of voltage, the stopping potential basically is equal to QV, the amount of voltage you add to it is equal to Ke max, okay? And so it's the same idea that this would be your cutoff frequency. And you can use these values, okay? So QV equal to HF minus your work function. By the way, this is phi, that's how you say that, okay? And so you can plug in these values. This right here is the charge on an electron, okay, 1.6 times 10 to the minus 19th coulombs, and use the voltage from the graph, okay? Once again, you can actually calculate your work function, because remember, this is our equation for work function, all right? Okay, we can use that cutoff frequency in order to calculate our work function, okay? So there's our cutoff frequency. We can use that in our equation. Okay, now that I've taken up all my space, let's see if I can get another sheet of paper. All right, so those are two graphs that you're going to commonly see. All right, let's go over our example. All right, it tells us that gold has a work function. I'll try to put it down the side column here. Gold has a work function of 4.82 electron volts. It says that a block of gold is illuminated with ultraviolet light, and it tells us the wavelength is 160 nanometers. Okay. It says find the maximum kinetic energy of the emitted photoelectrons in electron volts. Okay. Now, there is a Planck's constant that is on your constant sheet, which I don't have in front of me, so I'm not going to use it. That does give you Planck's constant in electron volts, so you don't have to convert. I'm going to go ahead and convert just for practice. Okay, so because Planck's constant is in joules, I'm going to convert my work function into joules. We know that for every 1 electron volt is 1.6 times 10 to the minus 19th joules. So my work function in joules is 7.7 times 10 to the minus 19th joules. Okay, it wants us to find the maximum kinetic energy. Okay, and remember that's equal to HF. So we're finding this. We know Planck's constant. We know the work function. We now need to find our frequency. And it did give us the wavelength. It said that it was 160 nanometers. And we have an equation that allows us to find our frequency. It's the speed of light, c equals lambda times frequency. Okay, so this is going to be 3 times 10 to the 8th meters per second is equal to 160 times 10 to the minus 9th times our frequency. And our frequency for our UV light is going to be equal to, let's see, where's that at? 1.88 times 10 to the 15th hertz. Okay, so guys, all we have to do is plug these values into our equation. So Ke max is equal to Planck's constant, 6.63 times 10 to the minus 34th, times our frequency, which was 1.88 times 10 to the 15th, minus our work function, which was 7.7 times 10 to the minus 19th joules. That's minus. So this is HF minus, let me move this up, sorry. So this is H times F minus phi. Okay, so Planck's constant times our frequency minus our work function. Okay, and we get a total energy that our electron has as it's ejected. Remember, this is the energy of the photon, and you're just subtracting the work function, which is the amount of energy that the metal has to absorb to eject it. And that's going to be equal to 4.76 times 10 to the minus 19th joules. And it wanted us to convert that to electron volts. So once again, there's 1.6 times 10 to the minus 19th joules for every electron volt. And you get K max in electron volts to be 2.98. So that's how much energy for part A that those electrons are going to have as they're ejected. Okay. The second part says find the threshold frequency for gold. Find the threshold frequency. Well, we have an equation for that. We know the work function. All we have to do is plug in Planck's constant to find the threshold frequency. So when we do that, we get 7.7 times 10 to the minus 19th joules equals 6.63 times 10 to the minus 34th joules times seconds times our frequency. And our frequency is equal to 1.16 times 10 to the 15th hertz. So that would be the minimum frequency that you would need to have in order to eject electrons. Actually, you would need to have that plus, like a little more at that work function.